Here's the next question, number 21. For the network shown in the figure below, the frequency in radians per second at which the maximum phase lag occurs is dash. Okay, so here we have been given a circuit, a network, and we have been asked for the frequency in radians per second. So frequency in radians per second is the angular frequency omega. So we need to find out the angular frequency omega. And in order to do that, we would first need the ratio of the output to the input in terms of S. So that will help us find out what the angular frequency is. So V naught of S by V in of S is what we need to find out first. Okay, so V naught of S. Alright, now let's look at the output here. So the output here is based on the resistance and the capacitance here. So resistance, it's across this, and we need it in terms of S. So that is R plus 1 by SC. It's R plus 1 by SC. So that is across the output here. Next, we need it in terms of the input. Now the input covers two resistance and capacitance. So here we would have total RT. I'm writing it as RT to indicate the total resistance plus 1 by SC. Now let's plug in the values. We have R here is just this value over here, 1. So that's 1 plus 1 by SC. C, we have the value of the capacitance as 1 farad. So here we have 1 plus 1 by S divided by, in the denominator here, RT is the total resistance, so that's 9 plus 1, so that's 10. 10 plus 1 by S. Now if we simplify this further, we will have the ratio of V naught by V in terms of S, of course, S plus 1 divided by 10S plus 1. Okay, so omega, the frequency, here is a very basic formula, an important formula. Omega is equal to 1 by T root A. It'll do good to remember this. Omega is equal to 1 by T root A. Now, the values of T and A will correspond to the coefficients of S in the ratio of output by input. So here is an important point. The value of T is the coefficient of S in the numerator. And AT is the term corresponding to the coefficient of S in the denominator. So if we are to look at the numerator over here corresponding to the output, okay, so T is the coefficient of S. So we see that the coefficient of S is 1. So from here we get that T is equal to 1. And AT corresponds to the coefficient of S in the denominator. So AT is equal to 10. If AT is equal to 10, then A is equal to 10. That's because T is 1. So A is 10. Now we have A is 10, we have T is equal to 1. Substitute these two values over here to find your omega value. So I'll put that down right here. Omega would be equal to 1 by root 10. So our final answer is omega is equal to 0.316 radians per second. Okay, so here is the value of the frequency in radians per second at maximum phase lag. So that's the point over here. So the formula for omega at maximum phase lag is 1 by T root A. So I hope this generalization has helped. Here's the next question, number 22. The direction of rotation of a single phase capacitor run induction motor is reversed by, option A says, interchanging the terminals of AC supply, B says interchanging the terminals of the capacitor, C says interchanging the terminals of the auxiliary winding, and D says interchanging the terminals of both the windings. Okay, so in order to change the rotation, the direction of rotation of a single phase induction motor, we will have to think about the rotating magnetic field. So the rotating magnetic field can be changed. When the rotating magnetic field directions are changed, then the direction of rotation of the motor is changed as well. So it all comes down to the magnetic field. So rotating magnetic field. So the direction of this rotating magnetic field can be changed in order to change the direction of the motor. And this can be done by interchanging not the terminals of AC supply, not the terminals of the capacitor, but the terminals of the auxiliary winding. So by interchanging the terminals of the auxiliary winding, we can change the direction of the rotating magnetic field and therefore change the direction of rotation of a single phase capacitor run induction motor. So the final answer and the right answer is C here, by interchanging the terminals of the auxiliary winding. Here's the next question, number 23. In the circuit shown below, the voltage and current sources are ideal. The voltage V out across the current source in volts is. Okay, so this is a multiple choice question. We have our four options, 0, 5, 10 and 20. In order to find the voltage across the current source, we need to find out the voltage in this branch here, because the voltage across this branch is the same as the voltage across the current source. So let's write the voltage equation. V out is equal to the voltage across this branch. So it is the voltage across this resistor here plus the voltage source here. So that's VR plus 10. VR is the voltage across the resistance. Now V is IR. IR plus 10. Now the current that is passing through this resistance here is 5 amps, because this is the current source and that's the current that is entering this resistor. So that's 5 into the value of the resistance is 2 plus 10. So that gives us 10 plus 10, which is 20 volts. So the voltage across the current source is 20 volts and it matches option D. I hope this has helped. Here's the next question, number 24. The graph associated with an electrical network has 7 branches and 5 nodes. The number of independent KCL equations and the number of independent KVL equations respectively are. Okay, so since they're talking about a graph, let's just assume a certain graph. So it says that there are 7 branches and 5 nodes. So in general, I'm just going to put down 5 nodes here. 1, 2, 3, 4 and 5. We have 5 nodes here. And the graph has got 7 branches. So let's see, that's 1, 2, 3, 4, 5, 6 and 7. Okay, so here are the 7 branches. So this is just, you can draw any kind of connections, give the connections as you wish, but in general I have put it down this way. And so we need to find out the number of KCL equations and KVL equations. So for current, it depends on the number of nodes that are there. So here, if we were to consider the fifth node as a base or a reference, so that would give us 4 different KCL equations. So KCL would be equal to 4. So that's 1 less than the total number of nodes that are there. So this is just an example. I'm not giving you a standard formula yet. I'm just explaining in terms of a random example. So we have 5 nodes. I've drawn a random graph here. So for which, if we were to find out the number of current equations, so those would be 4. And the number of voltage equations deal with the number of loops that are there in the graph. So here we see that there are 3 loops. That's 1, that's 2, and that's 3. So that's 3 loops. So the number of loops will give us the number of voltage equations. And the number of nodes would give us the number of current equations. And the number of nodes, the total number of nodes are 5. But then if we were to assume 1 as a ground node or a reference node, then the rest would correspond to the number of current equations. So I hope that makes sense. So now I'm going to give you the formula based on how to solve if you get something like this in the exam. So the number of KCL equations, okay, the formula is n minus 1. The total number of nodes minus 1. So in this case here, the total number of nodes 5. 5 minus 1 equals 4. So we have 4 KCL equations. And then comes KVL equations. Kirchhoff's voltage law equations. And Kirchhoff's voltage law corresponds to the number of loops in the graph. So based on what's given to us, the formula is B minus n plus 1. B minus n plus 1 is the number of loops. So the branches are 7 minus the number of nodes 5 plus 1. That gives us 3. Okay. So the number of KCL equations 4, the number of KVL equations are 3, and that corresponds to the option D. So it will do good to remember these formulas here, n minus 1 and B minus n plus 1. I hope this has helped. Here's the next question, number 25. 2 electrodes whose cross-sectional view is shown in the figure below are at the same potential. The maximum electric field will be at the point, okay, so we have 4 points here, A, B, C, and D. Now in order to find the maximum electric field at a certain point, you will have to see the distance of how far each point is from the other electrode. Now you see that the point C is the closest, point A is the farthest. So the options are somewhere between A and C. It could be point C or it could be point A. But here's the rule. Now you will have to remember at a certain point the electric field intensity is always maximum when the point is furthest away from the other plate. So I'll put that point here. The electric field intensity of a point is maximum when placed further away from the other electrode. So in this case, the right option is A. because point A is furthest away from the other electrode. Therefore, the maximum electric field will be at this point. The electric field intensity at this point will be maximum. Therefore, the maximum electric field will be at point A because it is further away from the other electrode. Here's the next question, number 26. The Boolean expression given simplifies to so and so forth. Okay, so the Boolean expression says A plus B bar, we read that as OR, so it's A or B bar or C or D bar, and B or C bar whole bar simplifies to one of these four options. So in order to solve this, the best way would be to remember some of the basic the basic formulas. So one of those is De Morgan's theorem. So I'll write that here. De Morgan's theorem, or one of those formulas, is A or B whole bar is equal to A bar and B bar. So let's keep this in mind while trying to solve and simplify that. Okay, so we have here A or B bar or C plus D bar or B C bar whole bar. Okay, so this can be written as, now the whole thing can be converted into this by using this theorem over here. So we have A or B bar or C or D bar and B or C bar, individual bars. Okay, so we have used De Morgan's theorem to write this into this expression here. Now this further can be written as A bar, B, C bar, D, B bar, C. Again, using De Morgan's theorem, we are splitting them into individual points using the same thing. Now another relation in Boolean expressions tell us that A bar and A equals 0. So here we see that we have C bar and C, we have B and B bar. So because of that, the entire expression results in 0. So this whole Boolean expression simplifies to 0. So the answer here is D. I hope this has helped. Here's the next question, number 27. For the circuit shown below, taking the op-amp as ideal, the output voltage Vout in terms of the input voltages V1, V2 and V3 is. Okay, so we have been given the circuit, the operational amplifier circuit here, with 3 inputs V1, V2, V3, and we are supposed to find out the output voltage in terms of these 3. So in order to write down the different equations, I have taken this point here and named it as VA. So the first thing we will do is use KCL and write down the equation at this node. So we would have VA minus V1 by 1, VA minus V1 by 1, that's our value, and next would be VA minus V2 by 4 plus VA minus V2 by 4 is equal to 0. So let's simplify this and see what we get. We get 4VA minus 4V1 plus VA minus V2 is equal to 0. That would give us 5VA minus 4V1 minus V2 is equal to 0. Okay. Let's write VA in terms of everything else. So from here we have VA is equal to 4 by 5 V1 plus 1 by 5 V2. So let's keep this equation in mind. We are going to use this for the next part of the solution. Okay, so the next thing is to write down the second current equation. Let's take the same point, but this time we will take the point here. So that's VA now. So VA, the second equation would be VA minus V3 by 1. Okay. VA minus V3 by 1. The next thing would be VA minus V out by the resistance in between, which is 9. So it's VA minus V out by 9 is equal to 0. If we are to cross multiply and simplify this, we will arrive at the equation 10 VA minus 9 V3 is equal to V out. So in this equation, let's substitute VA here. Okay. So when we do that, we'll be writing VA in terms of V1 and V2, and we will have the equation for V out in all of these three different voltages. Let me just get another piece of paper, sheet of paper. Okay, here we have. Right, so the equation is 10 VA minus 9 V3 is equal to V out. We have the previous equation for VA, so that would be 10 into 4 by 5 V1 plus 1 by 5 V2 minus 9 V3 is equal to V out. Let's open up the brackets and simplify. Further, we will get 8 V1 plus 2 V2 minus 9 V3 is equal to V out. So this is our voltage equation at the output. Okay, so let's see which part of this it actually matches. It matches number D, option D. So this is our final answer. Here's the next question, number 28. Let x1 of t corresponding to x1 of omega and x2 of t corresponding to x2 of omega be two signals whose Fourier transforms are as shown in the figure below. In the figure, h of t is equal to e power minus 2 mod t, denotes the impulse response. For the system shown, the minimum sampling rate required to sample y of t is the output here, so that y of t can be uniquely reconstructed from its samples is. Okay, so the question gives us four options, and I didn't have space to write it on this paper, so I've written it down on another sheet. Here are the four options: A to B1, 2 into B1 plus B2, 4 into B1 plus B2, and infinity. Now B1 and B2, you will notice, are here in the figure, B1 and B2, corresponding to the input signals x1 and x2 of x1 of omega and x2 of omega. Now B1 and B2 are the bandwidths. B1 is the bandwidth of x1 omega and B2 is the bandwidth of x2 omega. And the figure gives us that h of t, this system right here, is e to the power of minus 2 mod t. So correspondingly, you will see that the input signals x1 of t and x2 of t making up the system gives out the output of y of t. Now this tells us that the input signal, I'll write that here, the input signal is x1 of t into x2 of t. It's a multiplication corresponding to the equation given to us, e power minus 2 mod t. We get that from the multiplication of both the signals x1 of t and x2 of t. Now, since the question says that we need a minimum sampling rate, when they talk about minimum sampling rate, it is always good to think about the Nyquist principle. Now, we'll come to that. Let's look at the bandwidths first. Now, if the input signal is x1 of t into x2 of t, then the bandwidth, in order to get the highest frequency component, they are added. Now, that is an important point. I'll write that here. Okay, so we have bandwidth of x1 of omega is b1 and the bandwidth of x2 of omega is b2. And we also have that our input signal to the given system is x1 of t into x2 of t. So the bandwidths are added in order to get the highest frequency response. Okay, that's an important point. Bandwidths are added to get the highest frequency response. So this means that the bandwidth would be B1 plus B2. Now this is the general sampling rate, B1 plus B2. But because we are talking about the sampling rate, here the question says, the minimum sampling rate required to sample y of t so that y of t can be uniquely reconstructed. Now, since it talks about uniquely reconstructed and the minimum sampling rate, we have to remember Nyquist's principle of sampling rate. So, according to Nyquist's principle, let me write that down. According to Nyquist's principle, the sampling rate is twice the output bandwidth. So this is the bandwidth of the output B1 plus B2. According to Nyquist's principle, the sampling rate is twice the output bandwidth, which means it would be 2 times B1 plus B2. So this expression matches option B. So the minimum sampling rate required in order for the output y of t to be able to be uniquely reconstructed from the samples would be 2 into B1 plus B2. I hope this has helped. Here's the next question, number 29. The value of the integral minus infinity to infinity sine 2 pi t by pi t dt is equal to, we have our 4 options. Okay. So this integral will take a little bit of work. I'm going to walk you through it. Now, I always like using Laplace transforms as much as possible, since that is quite it's easier to deal with. So here we can use Laplace transforms in solving this. Okay, so we'll go step by step. Now let's consider the integral given to us. 2 times minus infinity to infinity sine 2 pi t by pi t dt. Okay, so let's use Laplace transform here, and let's consider this entire thing is equal to, say, some I. Okay, now look at the portion that is within the integral formula given to us. Sine 2 pi t by pi t. Now this is an even function. Now you know sine by itself is an odd function, but here since it is 2 pi t by pi t, the entire expression is an even function. So the whole thing here is an even function. Okay, so because it is an even function, we can write the integral. Just look at the integral over here. Because it is an even function, we can split the integral from minus infinity to infinity and write it as minus infinity to infinity, and we can write it as 2 times 0 to infinity. This is only because it is an even function. Okay, so we can split it this way. So let's write this now using this explanation. So we will have 2 into 2 times 0 to infinity sine 2 pi t by pi t dt. I hope this makes sense. Now this becomes 4 0 to infinity sine 2 pi t by pi t dt. Let's write this as equation 1. Now we'll take the part that is inside here, apart from the integral, just sine 2 pi t by pi t. Okay? Let's take pi outside. That's even better. We'll take pi outside and just consider sine 2 pi t by t. Just consider that part. Sine 2 pi t by t. So we are going to find out the Laplace of this. Okay? Now recall the formula. Laplace of f of t by t is equal to integral s to infinity Laplace of f of t ds. Now this is a formula that we will have to remember, okay? So keep in mind we are going to use this here. So if you notice, if you compare them two, you will see that f of t by t corresponds to sine 2 pi t by t. So in order to solve this, the Laplace of this is this, integral s to infinity Laplace of f of t, that is Laplace of sine 2 pi t. Let me just take another sheet of paper and we'll continue. Okay. Alright, so now we have Laplace of sine 2 pi t by t. Using the formula, we write it as integral s to infinity Laplace of f of t. So that's sine 2 pi t ds. Okay, so Laplace of sine, we know that s to infinity 2 pi divided by s square plus 2 pi square ds. Now you're quite familiar with this as well, but just in case, let me write that here. Laplace of sine a t is equal to a by s square plus a square. Okay? Alright, next. Let's see now what we have. We will have to use another formula. So let me write that formula down as well over here. This is an integration formula. Okay? So we have done this in intermediate, so I want you to just remember that. The integral of a by x square plus a square dx is tan inverse of x by a. Do you remember this? This is what we are going to use here, and it's quite similar. So that's what we are going to use. Okay? So integral of s to infinity 2 pi by s square plus 2 pi whole square ds. We relate it to this formula here, and we can write this as tan inverse of s by 2 pi. And this is from s to infinity. Now if we apply the limits, we get tan inverse of infinity minus tan inverse of s by 2 pi. If we are to solve this, we get pi by 2, that's pi by 2, infinity, minus tan inverse of s by 2 pi. So 90 minus tan inverse theta is cot inverse theta. So please remember that. That would be cot inverse of s by 2 pi. Okay, I'll write that here. 90 minus tan inverse theta is cot inverse theta. All various formulas. Okay, all of these are basics that we have learned during our intermediate. So we have to just incorporate all of that, including with what we have learned in linear algebra during our first year and second year of engineering, and apply all of that to problems like this. Indeed, it is a lot to remember, but with practice, you will get it all. So far we have cot inverse of s by 2 pi. Now, I think I'll just flip this around. I'll work it out over here. So the next step is, I'll just write that down here. We have L of sine 2 pi t by t is equal to cot inverse of s by 2 pi. This is what we have. Now let's substitute s is equal to 0. We'll substitute s is equal to 0. 0 to infinity sine 2 pi t by t dt is equal to, now we are applying the integral, okay? So integral of this would be cot inverse of 0 when we substitute 0 into this part over here. Now cot inverse of 0 is pi by 2. Let's call this equation 2. So now let's look at what we had at the very beginning. We had, I just take another color. Okay, 2 integral of minus infinity to infinity sine 2 pi t by pi t dt. This is what we started with, and we came to a point where we had 4 by pi 0 to infinity sine 2 pi t by t dt. Now integral of sine 2 pi t dt is pi by 2, right? That's what we have just worked out. This entire part is pi by 2. So this is I, what we started out with. Yes, okay. So here we have now 4 by pi into pi by 2. 4 by pi into pi by 2, that comes to 4 by 2, which is 2. Well, here is the final answer. The final answer is 2. I'll just note that down here. That's option number D. Well, I hope this has helped. Here's the next question, number 30. Let y of x be the solution of the differential equation d square y by dx square minus 4 dy by dx plus 4y is equal to 0. With initial condition y of 0 is equal to 0 and dy by dx at x is equal to 0 is equal to 1. Then the value of y of 1 is dash. Okay, so this is not a multiple choice question, so we have to work it all out. So let's start with the differential equation given to us. D square y by dx square minus 4 dy by dx plus 4y is equal to 0. So let's write this in terms of auxiliary equation. So we will have d square y minus 4 dy plus 4y is equal to 0, and the auxiliary equation becomes d square minus 4d plus 4 is equal to 0. We find out the value of d, the values of d from this equation here that is within the parenthesis, within the brackets. So we can use just the normal factoring methods. I'm sure you're quite familiar with that. This is a quadratic equation, so you can use any one of the many factoring methods that are there. You can use grouping, you can use quadratic formula, you can use completing the square method, whichever method is suitable to you. Here we can directly see that d is equal to 2 and 2. These are the roots. So the roots are equal and they are real. Now when the roots are equal and real, we write the general solution as, the general solution is written as y is equal to c1 plus c2x into e power ax, where a is the root that we have found 2. So c1 and c2 are values that we still need to find. Now c1 and c2 will remain as constants in the general solution. So we have here y is equal to c1 plus c2x into e power 2x. Okay, so this is our general equation, the general solution. Next step is to find out the particular solution. The particular solution is to find out the values of c1 and c2 using the initial conditions given to us. Okay, so I'll just grab another sheet of paper and then we'll continue. Right, so here we are. Okay, so we have the general equation, the general solution, c1 plus c2x into e power 2x. Now the first initial condition is y of 0 is equal to 0. If y of 0 is equal to 0, it tells us that y is equal to 0 and x is equal to 0. Let's substitute this over here. Sorry about that. It was just something that just slipped. Alright. So y of 0 is equal to 0 gives us two values. Y is equal to 0 and x is equal to 0. So from here, if we substitute both these values here into the general solution, we get 0 is equal to c1 plus 0 into 1, which gives us the value of c1 as 0. Now let's use the second initial condition. The second initial condition is y dash of 0 is equal to 1. If y dash of 0 is equal to 1, we have the solution here, right? We need to find out what the first derivative is. So let's differentiate the equation here. Y dash would equal to c2 e power 2x plus 2c2x e power 2x. Let me tell you how I got this. Now the equation is y is equal to c1 plus c2x e power 2x. What I've done is I've substituted c1 for 0, which gives us the equation y is equal to c2 x e power 2x. Now x into e power 2x, we can consider this to be UV formula. We use the derivative of the UV formula in order to differentiate. So y dash is equal to c2, which is the constant, it will remain the same. Okay, e power 2x and derivative of x is 1, plus c2 will remain the same. Okay, we are keeping x constant, we are considering x constant and then differentiating e power 2x. E power 2x is 2 into e power 2x, so that's 2 into e power 2x. This is our equation. Now y dash of 0 is 1, which means that y dash is 1, x is 0. So let's substitute that over here. 1 is equal to c2 e power 2 into 0 plus 2c2 0 e power 0, and that gives us, so that's 1 and that's 0, so here we have c2 is equal to 1. So we have our two values, c1 is equal to 0 and c2 is equal to 1. If we substitute both these values into the general equation, we will find the particular solution. So the particular solution, y is equal to, c1 is anyway 0, so we have c2. c2 is 1, so it is x e power 2x. So that's our particular solution. But the question asks us to find out what is y of 1. So y of 1 is equal to 1. It means that substitute 1 in place of x. This means x is equal to 1. So x is 1, e power 2 times 1. So the answer is e over 2, and that comes around to 7.38. Well, I hope the steps make sense and the answer is clear. So the final answer is 7.38. I hope this has helped. Here's the next question, number 31. The line integral of the vector field f is equal to 5xzi plus 3x square plus 2yj plus x square zk along a path from the origin 0, 0, 0 to 1, 1, 1, parameterized by t square t is dash. Okay, so this is not a multiple choice question, so we will have to work it out step by step to get the answer. Let's start with the vector field given to us. The field equation is 5xz I cap plus 3x square plus 2y j cap plus x square z k cap. And we have been given the point by which it needs to be parameterized. T square and t. Now since this is a three-dimensional plane, you can easily notice that it is three-dimensional, which means that here the first element corresponds to x, the second corresponds to y, and the third corresponds to z. So here we will have three expressions. X is equal to t, y is equal to t square, and z is equal to t. Now in order to work on this, since we are supposed to find out the line integral, we need to convert each one of this in terms of dt, t and dt. So that's what we are doing. So here, let's derivate each of these. We will get dx is equal to dt, dy is equal to 2t dt. We are differentiating, okay? And this is dz is equal to dt. So now we have our three expressions in terms of t, and we also have the derivatives. Okay, so the question says the line integral, so which means we need to integrate the entire function given to us. So let me write that in the next step here. Integral f dr. Now this is how we write the expression for the integral of a vector field. Integral of f dr. So this is from the origin 0, 0, 0 to 1, 1, 1. Okay. 5xz I cap plus 3x square plus 2y j cap plus x square z k cap dr. Now I am going to write the entire expression in terms of t. That is our parameter. Our parameter is t, therefore we completely express the equation in terms of t. Let me just grab another sheet of paper here and we will continue. Okay, alright, so now I'm going to write it here. Now since we are converting it in terms of one parameter t, we can write the limits of the integral from 0 to 1, just 0 to 1. So we have here the first term is 5xz dx. So we write that as 5t into t dt plus, now the second term is 3x square plus 2y. So this is t square and y is t square as well. 3t square plus 2t square and dy. So dy is 2t dt. We did that earlier. Plus the final term is x square z, if I'm not mistaken. Right, see, it's here x square z. Now x square z would be t square into t, so that's t cube. T square into t dt. So we have our expression. Let's simplify that. 0 to 1 phi t square dt plus, what do we have here? We have 3 and 2, 5, phi 2s are 10. So that's 10 t cube dt plus t cube dt. Okay, so let's add both these terms here. We get 0 to 1 phi t square dt plus 11 t cube dt. You can split this up here. Alright, so here now we can we integrate each term. So when we integrate 5t square, we get 5t cube by 3, 0 to 1, plus 11t power 4 by 4, 0 to 1. For each of these, the bottom limit, the lower limit 0 will bring the term to 0. So we can apply just the upper limit and we will get here 5 by 3 plus 11 by 4. 5 by 3 plus 11 by 4 is 53 by 12, and that gives us 4.416. So this is our final answer. Okay, so the line integral of the vector field is 4.416. That's our final answer. I hope it has helped. Okay, so here's the next question, number 32. Let P equals to 3, 1, 1, 3, which is a 2 by 2 matrix. Consider the set S of all vectors x, y such that a square plus b square is equal to 1, where AB equals P into xy, then S is, so our four options are a circle of radius root 10, a circle of radius 1 by root 10, an ellipse with a major axis along 1, 1, and an ellipse with a minor axis along 1, 1. So the first thing what we need to do is analyze the expression given here, AB equals P into xy. Since there's no space here, I'm just going to write it down on another sheet of paper. Right, okay. So we have AB is equal to P xy given, and P is given as 3, 1, 1, 3. So the first thing we do is plug this into the expression here. AB is equal to 3, 1, 1, 3 into xy. Now let's multiply these two. When we do that, we get 3x plus y. That's our first element, 3x plus y. And the second element is x plus 3y. So we're just multiplying these two matrices here. So this gives us AB is equal to 3x plus y, x plus 3y. If we compare both of these sides of the expression, we'll obtain two equations. So the two equations are A is equal to 3x plus y, A is equal to 3x plus y, and the second is B is equal to x plus 3y. There. Now, in the question, we have another relation. The condition given to us is that a square plus b square is equal to 1. Now that we have the expressions of a and b, let's plug both of these expressions into this condition here. This is the condition given. Now let's substitute both of this here. We'll get 3x plus y whole square plus x plus 3y whole square is equal to 1. Let's expand. We get 9x square plus y square plus 6xy plus x square plus 9y square plus 6xy is equal to 1. Simplifying it further, we get 10x square plus 10y square plus 12xy is equal to 1. Now this equation cannot be written in the form of, in the standard form of a circle, which means that the circle rules out. It does not represent a circle because we have here 10x square plus 10y square plus 12xy. We have an xy term. So we won't be able to split it in a way to get the standard form of a circle. Now I'm sure you're quite familiar with the standard form of a circle, standard form of an ellipse. So since we won't be able to write this in the standard form of a circle, the options A and B rule out. It is not a circle of radius root 10 and it is not a circle of radius 1 by root 10, which leaves out that it is either an ellipse with a major axis along 1, 1 or it is an ellipse with a minor axis along 1, 1. So let's simplify that equation further and see how we can write it in terms of the standard form of an ellipse. Okay, so right, I'll write it here. The equation is 10x square plus 10y square plus 12xy is equal to 1. Now if we split this and rearrange it, we can write it in terms of x plus y and x minus y. We will get 8 into x plus y whole square plus 2 into x minus y whole square is equal to 1. So that part of it, I will leave it to you. If you split it, add terms and subtract terms, you will be able to get 8 into x plus y whole square plus 2 into x minus y whole square is equal to 1. Now let's write it in the general form of an ellipse. Now you're quite familiar with the general form. The general form is x square by a square plus y square by b square is equal to 1. This is the general notation. So if we were to rearrange, we'll bring the 8 down and the 2 down here. So we will get x plus y whole square divided by 1 by 8 plus x minus y whole square divided by 1 by 2 is equal to 1. So now we have it in the form of an ellipse equation. Now if we compare this with the standard form, we see that the value of A is 1 by 8 and the value of B is 1 by 2. And the numerator, the first part, corresponds to the major axis length, and the second corresponds to the minor axis length. Okay, so here we have A is less than B, 1 by 8 is less than 1 by 2. So the major axis length is x plus y is equal to 0. The major axis lies along this and the minor axis length lies along x minus y is equal to 0. So now if we say x plus y equals 0, what does that give us? That gives us x is equal to minus y. And if x minus y is equal to 0, that gives us x is equal to y. Now here's the thing. If it is x is equal to minus y, here's our axis. We have x here, we have y here. This is our xy plane. X is equal to minus y is along here. It passes through the origin. So here we have x is equal to minus y. And this line right here represents x is equal to y. Now for x is equal to minus y is the major axis length, or the major axis lies along this, which means that the ellipse is something like this. Here is our minor axis. This is our major axis. So the major axis tells us that the value is 1 minus 1, because y is minus 1. It's a negative. So it is 1 minus 1. But for minor axis, it is 1, 1. It is positive. So this gives us the answer. It means that the ellipse's minor axis lies along x minus y is equal to 0, which gives us x is equal to y, and x and y are positive values. So that's our final answer here. Let me just write. So the final answer is D, an ellipse with a minor axis along 1, 1. I hope this has helped. Here's the next question, number 34. The driving point input impedance seen from the source Vs of the circuit shown below in ohms is dash. Okay, so this is not a multiple choice question and we will have to try and work it out. So in the circuit given to us, let's take the point A as shown. Now the question talks about driving point input impedance. So the driving point input impedance, I'll call it dz, is defined as the ratio of the EMF of the source to the current of the source. So which means that dz can be written as Vs by Is. Now Vs is the source voltage, which means that here is our Is, current that is passing through this branch over here. So let's take the point A and try and write down the KCL. We'll apply the KCL at point A and we'll write down the current equation and see how it goes from there. So applying KCL at point A. Okay, let's see. Now, if we apply it at point A, we see that Is is through that branch there, Is plus. Now here we have a current source and the direction of current is upward, therefore it would be plus 4V1. Okay, minus. Now we are going to take a look at this branch and this branch here. So it is VA by 3 minus VA by the sum of the resistances in this branch. So that's 4 plus 2, VA by 4 plus 2 is equal to 0. Now this is our current equation for the entire circuit at that point, at that node A. So we now have Is plus 4V1 minus VA by 3 minus VA by 6 is equal to 0. Now let me simplify this even further. I'll put it down over here. Is plus 4V1 minus VA by 3 minus VA by 6 will give us VA by 2 is equal to 0. So here is our basic current equation of the circuit simplified. Next, let's look a little further at the circuit. Now V1 is the voltage across that resistance there. That's what's given in the circuit, V1. And here the current that is from this current source is 4 times V1. So if we were to calculate just that corresponding to what is given over here, we can say that let's look at just the resistance there. V1 is the voltage across that resistance and 2 is the value of the resistance and Is is the current passing through that resistance. So using just that portion we can write down one expression. So the expression is V1 is equal to 2 times Is. So we know that V is equal to IR. R is 2. I is Is. So this is one relation. V1 is equal to 2Is. Now the next relation, let's look at, we need to eliminate VA over here. In this equation, we have Is, we have V1 and we have VA. V1, we can write it in terms of 2Is. Now we need to try and eliminate VA. So let's look at this circuit once again and try to write down an expression for VA in terms of Is. So what we can do is, let's look over here. So VA, just the voltages. Okay, we'll look at just the voltages. So we have VA is equal to Vs minus V1. If we were to look at just this portion over here. So that gives us our second equation, second relation. VA is equal to Vs minus V1. Now V1 is 2Is. So that gives us VA is equal to Vs minus 2Is. Let's call this 1, let's call this 2. So now we have two relations. We have VA and we have V1. So let's substitute both 1 and 2 into this equation here. Alright, I'll write this down here now. So the equation is Is plus 4V1 minus VA by 2 is equal to 0. Now we substitute Is plus 4 into V1 is 2Is minus VA is Vs minus 2Is divided by 2 is equal to 0. Let's simplify this even further. We get 2Is plus 8Is minus Vs plus 2Is is equal to 0. This is times 2. So we further get this as 2Is plus 16Is minus Vs plus 2Is is equal to 0. Now we have 20Is minus Vs is equal to 0. Now the question asks us to find out the driving point impedance ZD, and we saw that by definition ZD is Vs by Is. So using this relation we can write this as Vs by Is is equal to 20 by 1. If we take this to the other side and rearrange the terms a little bit, we'll get Vs by Is is equal to 20 ohms. This is our final answer. Right, it's not a multiple choice, so it's 20 ohm. I hope this has helped. Here's the next question, number 35. The Z parameters of the two-port network shown in the figure are Z11 is equal to 40 ohms, Z12 is 60 ohms, Z21 is 80 ohms, and Z22 is 100 ohms. The average power delivered to RL is equal to 20 ohms in watts is dash. Okay, so this is again not a multiple choice question. Let's work it out. Alright, so to begin with, we'll write down what's been given to us. We have the Z parameters given. The values of Z11 is 40, Z12 is 60, Z21 is 80, Z22 is 100. So these are the Z parameters given. Now let's look at the figure here. We can write down equations for V2 and V1. That's what we must do. So let's look at V2 first. Now V2 is equal to, let me just write that, V2 from the figure, V2 equals minus I2 RL. Look at the direction of the current. That's important. Okay, so here we have minus I2 into RL, which is minus 20 I2. That's because the value given for RL is 20. So minus 20 I2. Let's call this equation 1. Now let's write down the equation for V1 in terms of the Z parameters. Now you're quite familiar with how to do this. We write this as V1, V2 is equal to Z11, Z12, Z21, Z22 into I1 and I2. This is how we write the matrices in terms of the voltages, the Z parameters and the current given to us. Now from this, let's write down our two equations. Our two equations would be V1 is equal to Z11 I1, we are multiplying, okay, plus Z12 I2, V2 would be Z21 I1 plus Z22 I2. So these are our two equations. Now we have the values of Z, the Z parameters given to us. Okay, so let's substitute that, and we also have V2 in terms of I2, minus 20 I2. Okay, so let's start with this. Let me just take another sheet of paper. Right. Okay, so we have the equation V1, Z11 I1 plus Z12 I2. We'll substitute the values. We get V1 is equal to 40 I1 plus 60 I2. Let's call this equation 2. Next, we have V2. V2 is equal to Z21 I1 plus Z22 I2. We have our values for Z21 and Z22. Let's substitute, including the value for V2. V2 is the expression from equation 1, which was minus 20 I2. So that's minus 20 I2 is equal to 80 I1 plus 100 I2. Let's call this equation 3. Now if we simplify this even further, we'll get a relation of I2 and I1 in terms of each other. So that's minus 120 I2 is equal to 80 I1. I2 is equal to minus 80 by 120 into I1. We can simplify that and write it as minus 2 by 3 I1. So I2 is equal to minus 2 by 3 I1. Let's substitute this into equation 2. Let's substitute that into equation 2. So what will we get? We'll get V1 is equal to 40 I1 plus 60 I2, right? So in terms into I2, let's plug this in. We'll get 40 I1 plus 60 into minus 2 by 3 I1. So this results in 40 I1 minus 40 I1, which is 0. So this means that the value of V1 is 0. Now let's go back to the figure and look at just this loop over here. Just this loop. We have I1 here. So in this loop we see, we can write our voltage equation 20 plus 10 I1 plus V1. Let me write that down. Right. Okay. So from the first loop, I'll write that from the figure, this is for loop 1, the first side of the loop. we can write down the voltage equation, and the voltage equation is 20, that's the source, is equal to 10 I1, that's the voltage across the resistance, plus V1. Now we know the value of V1, we just found it to be 0. So let's substitute that and solve. 20 is equal to 10 I1 plus 0, which gives us the value of I1 to be 20 by 10, which is 2 amps. Now that we have the value of I1, we can easily find the value of I2. I2 is equal to minus 2 by 3 I1. That's the relation that we found here. Minus 2 by 3 I1. So let's substitute. Minus 2 by 3 into 2, which gives us minus 4 by 3 amps. Now the question talks about the power dissipated. Now the power dissipated to here. See, the power delivered. The power delivered to the resistance, the load resistance of RL. So the power equation is VI. So the voltage and the current across that resistance is what we need. And we see from the figure that the voltage is V2 and the current is I2. So that is what we need. We need V2 and we need I2. We have our I2 here. We also have the relation of V2. Right, so in fact, we don't need V2. Let's just use RL instead. You can use any power formula, whatever comes to your mind, really. So we know the power formula is VI. We also know that it is I square R, and we also know that it is V square by R. So either one, any one of these you can use. It's not a problem. So in this case, let's use I square R. So we have the power to be I square is I2, because that's the current that is passing through the resistance, the load resistance. So that's minus 4 by 3 whole square into R, which is 20. So solving this, we get 16 by 9 times 20. 35.55 watts. So this is our final answer. The power delivered to the load resistance is 35.55. Here, 35.55. So this is the entire solution, and I hope it has helped.